everybody, welcome back to Mathematical Statistics. Today is our last full day. On Wednesday, we're going to mostly review for the final, but I do reserve the first 15, maybe 20 minutes to tie up some loose ends. So yeah, let's just get into it. We are GLRTing. GLRT, GLRT, stands for Generalized Likelihood Ratio Test. And this is just another form of hypothesis testing. We had the I'm just going to guess at a statistic and a direction. We had the UMP test, uniformly most powerful tests, which are the greatest things you can do, but they can be difficult to find and they don't always exist. And then we have the GLRT. So all three of these methods have us picking out a statistic somehow and a direction, or what we're going to do with that statistic. I'm going to reject if my statistic is in this particular region. And the GLRT, no exception. But I think the strength of the GLRT is what we're going to talk about today, and that is once you have your statistic and a direction, you need to find cutoffs using alpha, and that involves computing probabilities that in real life could be quite difficult. So what we're going to do today is talk about large sample GLRTs and approximate GLRTs using asymptotic properties of the generalized likelihood ratio so that we can do something approximate even if we can't solve things exactly. So for my first example, I just want to do not one of those. So I just want to do one more example where we do the test exactly, but it's going to be our first example where we have the parameter in the indicator. So how about IID uniform 0 theta? Now I'm going to do something kind of funny here. I'm going to close this interval on the right. I usually don't do that. It doesn't change the distribution because the PDF has no area at that single point, but it will make something kind of convenient in my hypothesis test, as you will soon see. So let's find the generalized likelihood ratio test of size alpha for testing the null hypothesis that theta equals theta naught versus the alternate hypothesis that theta equals theta 1. So like I said, there's nothing new in this example except for the parameter being in the indicator, but let's take the same approach. So the first thing you would want to do is write down the likelihood function. We usually call this capital L of theta. This is going to be 1 over theta to the n and a product of a bunch of indicators, putting each xi between 0 and theta. As we've seen, we can rewrite this product of indicators in at least 2 more ways. And when working with MLEs, such as in the GLRT, it's convenient to go as low as we can, factoring those indicators or rewriting the indicators so that we have the fewest thetas that we can have. So you can go straight there. I think you probably know what I'm going to do, but one way I can rewrite this is the indicator that says that the minimum is in that interval times an indicator that says that the maximum is in the interval. But for forming a likelihood, we need to keep all the theta parts, and both indicators have theta in it. So note that we can rewrite this, and we can say that the minimum is somewhere between 0 and the maximum, and therefore we have a piece with no theta that can be dropped in the likelihood, and the maximum is between 0 and theta. So I shouldn't have written this equals because I haven't chosen my likelihood yet. So this is really the joint PDF up here, and then I'm going to choose the third one to be my likelihood, this sort of simplest one. So maybe write that, sorry about that. The likelihood L of theta, I'm going to take it to be 1 over theta to the n times this final indicator over here. This is constant with respect to theta. So we get 0 to theta of the maximum. Okay, so for a GLRT, we need to find the maximum likelihood estimator. I'm not going to do that. We've done that so many times for this problem. This is one of those problems where you take a log and take a derivative and set it equal to 0, and you don't find any critical values, but then you say, hey, I still want to maximize this. This is an increasing or decreasing function of theta, so let me look at the endpoints, and we get that the MLE is the maximum value in the data set. Then for a GLRT, we need the restricted MLE. We call this theta naught hat. And this is going to be whatever maximizes this likelihood when the null hypothesis is true. But in this problem, the null hypothesis consists of a single point, so there's not many points to look at. It's going to be maximized and minimized and everything at that single point. So the restricted MLE is just that fixed known value theta naught. Okay, let's form the generalized likelihood ratio. We're calling this lambda of x. This is the likelihood at the restricted MLE over the likelihood at the regular MLE. This might look a little weird to you because I have no x's in the right-hand side, but the notation is suppressed. Not only do likelihoods depend on x, but the MLEs certainly depend on x as well. So there are definitely x's in there. And I am going to write this out. So I'm going to end up with, when I think about that theta in the denominator, I'm going to end up with the maximum over theta naught to the nth power. So I've already kind of flipped things. And an indicator that says that, so I'm plugging in for theta, my restricted MLE. So it's going to be 0 to theta naught. I guess I've started to capitalize my maximum. Let me not do that yet. It doesn't matter, but I need to be consistent at least in the equation. Over the indicator from 0 to theta, and I'm plugging in the MLE, which is the maximum, and plugging the maximum in. So here's where I close that bracket for. Note that the maximum is always in this interval as long as the interval includes the maximum. So what that means is that this entire indicator is always 1, and we can drop it. And again, I didn't change anything by including that right endpoint because the distribution is still the same whether or not you include that endpoint. So yeah, I did it for convenience. And we have a generalized likelihood ratio. So the rule here, the GLRT, is going to be to reject the null hypothesis in favor of the alternative if this lambda of capital X, which is the random capital maximum over theta naught to the n, times an indicator that puts the maximum between 0 and theta naught. I want to reject if this is less than or equal to k. That's the form of the GLRT. So what we usually do next is we try to kind of solve down and isolate the x on the left-hand side, or the statistic involving the x's, to get a statistic and an inequality and something maybe where we can solve for a new constant that came up along the way. We usually say, okay, my constant is now a k1, now a k2 as you're simplifying. So yeah, this is hard because I kind of want to take the nth root of this, but then I have to take the nth root of this. I guess that's not bad because indicators are 0 or 1. So the nth root is also 0 or 1. So I guess that really doesn't matter. But I'm definitely not going to get this as a single instance of that statistic, the maximum on the left-hand side, because the maximum is appearing in sort of two places on the left-hand side that are not going to combine very easily. So I am going to work with this entire expression. And this is something that you often have to do when you're finding a GLRT and the parameter is in the indicator. Let's find k. Alpha is going to be the probability of a type 1 error, and this is the maximum probability of rejecting the null hypothesis when you shouldn't because it's true. This maximum is taken over all values in the null hypothesis of the parameter, but we only have one here, theta naught, so we don't really need to compute any maximum. So this is going to be the probability that we reject the null hypothesis when it's true, meaning that the parameter is theta naught. And rejection, we've got this kind of messy looking rule here, but I'm going to fill it in. And now let's see what we can do. We are under the assumption that the null hypothesis is true and the parameter is theta naught. If our data x1 through xn is IID uniform on 0 to theta naught inclusive, then all of our x's, including the maximum, are less than or equal to theta naught. That means that this maximum is always in this interval. Again, the reason I closed the interval. So this is 1 when the null hypothesis is true. It's not 1 in general. That's why I didn't simplify it, but it is 1 in this calculation. So let's rewrite this. Okay, so now I have just a single statistic, the maximum on the left-hand side. I am going to take the nth root on both sides, and I am going to multiply across by theta naught. So I'm going to keep track of my constants just for a moment. I'll get less than or equal to theta naught k to the 1 over n when the parameter is theta naught. Can you call this k1? Absolutely. Do you want to? Usually when we rename the constant, it's because we're coming up with a simpler rejection rule and we don't care about what we had above, but we can't ignore the fact that the rejection rule does involve an indicator which will not disappear in general. It will only disappear when this null hypothesis is true. I'll show you what I mean. I'm going to call this K1 for just a brief period of time. And let's write out this probability. It is a maximum, so if you know the CDF for the maximum, go straight for it. Because things are IID here, I do know this is the probability that one of them is less than or equal to K1 to the nth power. And we're talking about a uniform 0 to theta naught, so the PDF is 1 over theta, and the probability or less than or equal to K1 is that base of the rectangle K1 times 1 over theta. So we get K1 over, theta naught to the nth power, and all of this was equal to alpha. So let me just recap that there. And so we want to find K1, I'm going to take the nth root on both sides of this. I'll get alpha to the 1 over n, and then I'm going to multiply the theta naught over. Okay, so here's where you have to be careful. This is our rejection rule, but really only if we know the null hypothesis is true. So if I write, and maybe you don't want to write this because it's going to be wrong, I'm telling you right now, reject the null hypothesis in favor of the alternative if the maximum is less than or equal to theta naught alpha to the 1 over n. Does this seem right to you? I already gave it away, but our hypotheses are theta equals theta naught versus theta does not equal theta naught. So we want to reject if our theta naught, if our right endpoint for this distribution seems too low or seems too high. And so I wouldn't expect a one-tailed test like this, a test with just one direction. And the reason is because this circled thing on the board right now is not the actual rejection rule. It was a simplification allowed only when the null hypothesis is true, but you don't do a hypothesis test knowing that it's true. So I have to go all the way back up to this rejection rule right here using my K. And my K is related to K1. So here was the relationship. So this is K1, and K1 was theta naught K to the 1 over n. So let's use this to go back and find K. Whether you actually solve this or just look at it, it's easy to see, if this has to match this, that K is going to be alpha. And maybe looking at it was the wrong thing to do. Go ahead and plug in K1 for K and actually solve this, but you will get that K equals alpha. So here is the GLRT. The GLRT of size alpha for the null hypothesis that theta equals theta naught versus the alternate hypothesis that theta does not equal theta naught for the uniform zero theta distribution is to reject the null hypothesis in favor of the alternative if the maximum over theta naught to the n times the indicator that says that the maximum is between 0 and theta naught inclusive is less than or equal to k, but we determined that k was alpha. So this indicator is going to automatically knock the null hypothesis out of the running. And this corresponds to, consider this. If you have your theta naught sitting on a number line and you take a sample and the maximum is above theta naught, you know for sure that the null hypothesis can't be true because all the values had to be below theta naught. That's what's happening here. If the maximum is greater than theta naught, then it's not in the interval for this indicator. So the entire left-hand side of this inequality is going to be 0, and that is definitely less than any alpha we choose. And so automatic rejection when we should have an automatic rejection. And so we're done. There's our GLRT. Parameters in the indicator, those have always been the tricky cases for us. And they take some thought, a little less plug and chug than all of our other cases, no matter what we're doing in math stat. Okay, so we're ready for the exciting new result for today. It is known as Wilks's theorem. This is an asymptotic result, which tells us how a simple function of the generalized likelihood ratio should behave when the null hypothesis is true as the sample size goes to infinity. So here is the setup. Suppose I have x1 through xn, IID from some distribution with a PDF, f of x and theta, and I'm going to assume that theta is k dimensional. For us, they've mostly been 1 or 2 dimensional, but they can be more than that. And I want us to consider finding the GLRT of size alpha for a null hypothesis that is going to be kind of specific. Let me first write it kind of not specifically. Theta is in some capital theta naught versus theta is in the rest of the parameter space, where this theta naught has a specific form where it fixes some of the parameters. And then the alternate hypothesis is not the null hypothesis. As an example, maybe k is 5, so maybe we have 5 parameters. This is kind of realistic when you start doing statistics that looks like regression models or Bayesian statistics. And the null hypothesis might be that theta 1 is 3 and theta 4 is -2. And then the alternate hypothesis is something goes wrong there. At least one of those is not true. So these are the kinds of hypotheses that can be tackled using Wilks's theorem, which I still haven't stated. So consider this the sort of subject heading, not my actual theorem, because I do need to set up some notation. So I'm going to start that over. Sorry about that. So I'm going to let L of theta be a likelihood, and you would then, this is a generalized likelihood ratio test. So you would have to find an MLE and a restricted MLE, and from that you could form the generalized likelihood ratio. And so here is Wilks' theorem. Under certain regularity conditions, now we will hit these as we go, but one of them is definitely the parameter is not in the indicator. So if that is the case, you should not be trying to use Wilks' theorem. Under certain regularity conditions, -2 times the log of the generalized likelihood ratio, and I want to make this capital because this is a convergence result, a convergence in distribution result. It converges to a chi-squared critical value with k minus k naught degrees of freedom. I need to define these. So let me up here say that theta is k-dimensional, and over here say where k naught is the number of free parameters when the null hypothesis is true. So in other words, this could be written as just the number of fixed parameters under the null hypothesis. But for reasons, it's usually written this way. I would say bear with me for now and we'll figure it out, but we're almost out of time in this course. But yeah, if you want to write that degrees of freedom as the number of fixed parameters, go ahead. Now we're going to prove this result, but first I'd like to do an example just to show you why this is such a great result to make your life easier when GLRTing. Okay, so let's try an example and then we'll go back to prove this. Let's consider x1 through xn, IID, normal, mu, sigma squared, where these parameters are both unknown. Now, this isn't a place where I would probably use Wilks' theorem because for the normal distribution, we can usually solve these problems exactly. But you'll see even for this case that it is really a mess. So it's just an example. But suppose I want to test that mu is mu naught versus mu does not equal mu naught. Now this would be a t-test if we were just doing a straight up regular common sense hypothesis test or even the UMP test because we don't know sigma squared. So we'll probably use the sample variance as squared and this will involve a t-distribution. But here I want us to find an approximate large sample GLRT of size alpha. So I could use any distribution here. I'm just using this one. And usually you wouldn't be able to say, I know this is a t-test. Usually you're not going to know what kind of test it is. And when you try to start GLRTing, it will become intractable. And that's when you want to use Wilks' theorem, assuming the parameter is not in the indicator. Okay, so the likelihood is a function of mu and sigma squared both, because they're both unknown. And this is sigma squared to the negative n over 2, and you could put a 2 pi in there if you want. It will cancel when we form that ratio. E to the minus 1 over 2 sigma squared, the sum as I goes from 1 to n of xi minus mu squared. That's our likelihood. And the MLEs, by MLEs, I mean unrestricted MLEs. Mu hat is x bar, and sigma squared hat is not the sample variance. Some people will say that because we define sample variance so that it was unbiased. But the MLE is actually the biased version of the sample variance. And as I've said many times in this course, some people will also call this capital S squared, but we've been using capital S squared for a similar expression when we have n minus 1 in the denominator. Okay, so restricted MLEs, as I goes from 1 to n of xi minus mu naught squared over n. Let's form the likelihood ratio. I don't know, capital, lowercase, I'm going to go capital, I guess. This is going to be the likelihood at the restricted MLEs over the likelihood at the regular unrestricted MLEs. The likelihood is right here. So let's plug in. I'm not sure I want to write this whole mess down. I think I should, though. I'm going to make a mistake if I don't. So I'm going to keep that negative exponent and everything. In the numerator, I'm going to put the sum of the xi minus mu naught squared over n. Raise that to the negative n over 2 e to the minus 1 over 2 sigma squared. So that's going to end up being e to the negative n over 2 sum xi minus mu naught squared. Did I say sigma squared? I mean the MLE sigma naught hat squared. And then I'm taking this and I'm plugging in this MLE, and that will be the sum of the xi minus mu naught squared. And all of that is the numerator for the generalized likelihood ratio. The denominator is going to look the same, except that all of those mu naughts are going to be x bar. Let me just copy and paste here. I'm going to get x bar here, and x bar here. Those e's are pretty nice. Look what's happening. This is canceling with this, and this is canceling with this. And so as far as the e part goes, I have e to the negative n over 2 divided by e to the negative n over 2. So what's left for the e's are going to completely cancel. That's actually kind of nice. And for the other part, I am going to flip some stuff. Let's write this as the sum of the xi minus mu naught squared over the sum of the xi minus x bar squared to the negative n over 2. I did cancel the n's, and that is looking pretty simple. Okay, so we want to reject the null hypothesis if this is less than or equal to some k, where k is to be determined. And the x's are here and within squares and within sums, so it's not easy to pull stuff together into a simple statistic. Maybe we can figure out maybe we can set this less than or equal to k and then take care of this, move it around to the other side, and find the distribution of this, but that will be difficult because the x's in the numerator are dependent on the x's in the denominator. For the normal distribution, we will eventually get there, but we're lazy, we don't feel like doing it, or we're doing a non-normal problem where we just can't do it. So in this exercise, I asked you to find an approximate large sample GLRT. That's your clue that there's an asymptotic result here. We're going to reject the null hypothesis. I'm going to write this again. So we're going to reject the null hypothesis if lambda of x, or GLR, is less than or equal to k. But let's take the log on both sides, which is not going to flip the inequality. And let's take -2 on both sides, which is going to flip the inequality. So we'll end up with -2 log the generalized likelihood ratio greater than or equal to a new constant k1, which is -2 times the log of k. This is now the rejection rule, and it would be what we would do if our sample size went off to infinity, because it's an asymptotic result. It's a convergence in distribution result. But we're going to go for the approximate. We're going to say we have a large sample. We think it's close enough to infinity. And so this is only an approximate test. So, ooh, what a poor choice of letters here. So I have a K and a K1 for my degrees of freedom for the chi-squared distribution. So I'm just not going to write any letters. The number of parameters in this problem is 2, the mu and sigma squared. The number of free parameters, I do have a reason for saying it this way. Hopefully I can use my 15 to 20 minutes at the beginning of the next class to talk about that. But the number of free parameters when the null hypothesis is true, that null hypothesis nails down mu, so we just have sigma squared free. This is 1. And so the number of parameters minus the number of free parameters is 2 minus 1, or 1. So minus 2 times the log of the generalized likelihood ratio is converging in distribution to a chi-squared 1 by Wilks's theorem. And we do not have an infinite sample size, but we're going to say that for a large sample, everyone reverts to the n greater than 30 or 40, but that's really only a result for the central limit theorem. And even that may not work for certain underlying distributions. It's underlying distribution dependent, but I'm never going to try to catch you on this. So on the final, I'll say you have a sample of size 100 or maybe even more than that. So for this large sample, -2 log times the GLR is approximately, I didn't write asymptotic, this is our approximate notation, approximately chi-squared 1. Okay, so what is going to be the final rejection rule? Alpha is the probability we reject a null hypothesis when it's true, because we just have a simple null hypothesis, so there's no maximizing. This is the probability that lambda of x is less than or equal to k when the null hypothesis is true. This is the probability that -2 log lambda is greater than or equal to k1 when the null hypothesis is true. And this is approximately a chi-squared 1 random variable. If I look at the chi-squared 1 PDF, then I want a number that we are above with probability alpha. And that number is going to be our chi-squared alpha comma 1 critical value. So our test, the approximate large sample generalized likelihood ratio test, is to reject a null hypothesis if -2 times the log of the generalized likelihood ratio is greater than or equal to this chi-squared critical value, where it's already written here, but if you write this, you better make sure that you've given someone the GLR. If you want to go and plug that in to make your test look more mysterious and fancy, then go ahead and do it. But the thing I've circled here is fine as long as you've defined the lambda somewhere. That's it. That is it. And the log is always nice and monotone, and the -2 multiplying is always going to flip things. So your tests are always going to look, your large sample approximate GLRTs are always going to look like this. It's just that the degrees of freedom may change depending on the number of parameters there are overall and the numbers that are fixed. And that's it. Super easy. Barely an inconvenience. Also super approximate. I like to do things exactly when I can. But you'll notice if you use, say, R software to do a numerical hypothesis test, you're often going to be, it's going to report to you chi-squared critical values, and it's probably using an approximation like this in the background. Okay, so let's prove Wilks' theorem. Just to keep this short and sweet, I'm going to only prove it for a one-dimensional parameter, so k is 1. And the null hypothesis is going to be that theta equals something versus the alternative that theta does not equal something. So that means there's no free parameters when the null hypothesis is true. And we should get that -2 times the log of the generalized likelihood ratio converges in distribution to a chi-squared 1. I'm not going to do the general dimension case. Now, I did say there were certain regularity conditions that we're going to need. So number 1 is no parameter in the indicator. Once you have that, you cannot use Wilks' theorem. The second is that the theta naught, so I didn't write it, I said it, but the null hypothesis is going to be theta equals theta naught versus the alternate that theta does not equal theta naught. So theta naught needs to be in the interior of the parameter space. So if you have some distribution that says that theta has to be between 1 and 2, just to make something up, theta naught had better not be 1 or 2. It needs to be inside in the interior of the parameter space. The third regularity condition I'm going to need is that the derivative with respect to theta of the joint PDF, I'm going to need this to exist. I don't know why I'm writing these out right now. I should probably do what I usually do, which is start to prove it and then pick off things like, well, if this was true, then we can do the next line. But I've started and I only have 2 more, so let me just finish this up. The one-dimensional Fisher information, or the n-dimensional Fisher information could go here as well. When the parameter is theta naught, needs to be greater than 0 and also finite. Going to be in a denominator. We don't want any zeros in a denominator. We also don't want, we want actual numbers in there and not infinity. And the final one is that, so this lowercase l is my log likelihood, you'll recall. I'm going to take a third derivative, look at it not at theta naught, but as a function of theta. I need this third derivative to exist and be bounded in a neighborhood of theta naught. And there is a neighborhood of theta naught within the parameter space because theta naught must be in the interior of the parameter space. All right, so now I'm a little torn. I'm a little torn about how rigorous this proof is going to be. What you're about to see looks a lot like when we proved asymptotic normality for MLEs. And I said at that point, oh, this goes to 0 really fast. And I kind of like to say it a little bit better. I don't know if I have time. I think I have time. So here are a couple of definitions for you. If you have a sequence of random variables, xn, and you have real constants like lowercase an, if you see someone writing xn equals, and then a lowercase o sub p of an, so we say that xn is little o p, or I'm going to write p, no one laugh, of an. This means that if you take the sequence of random variables and you divide by the constants, that this converges in probability to 0. It's a way to say that the xn's are getting small. And in particular, we're going to need to talk about xn being little op of 1, which means that my xn's are converging in probability to 0. I don't have to divide by anything. You may have seen little o notation in other parts of analysis without the subscript p. You might have seen little o and big O functions or terms. If you haven't, that's okay. We're kind of doing it from scratch here, but this is a probabilistic version of what you may have seen before. So when I want to say plus a term that goes to 0, I'm going to write something like this. And this equals is kind of misleading. You really need to read that as is. And then we get all sorts of cool arithmetic, like, here's a little fact for you. Little op of 1 plus little op of 1 equals little op of 1. The point I'm trying to make, I'm not doing a good job, I'm rushing here, is that this represents some function with a property, and this represents some function with the same property, but not necessarily the same function. And I claim that if you take a sequence of random variables that converges in probability to 0, and another sequence, so like you have xn converging in probability to 0 and yn converging in probability to 0, then xn plus yn converges in probability to 0. We've actually already seen that result. So this side should not be 2 little op of 1. It's just a new function that has this property that it is converging in probability to 0. So this is just a way to wrap up all your terms at the end of Taylor series expansions and feel less guilty about saying stuff that goes to 0. It's kind of leaving off a lot of detail, but it's the formal way to do it. Okay, so I have another definition for you. A sequence of random variables xn is bounded, this is what I'm defining, bounded in probability if for every epsilon greater than 0, there exists a constant m, and this m will most likely depend on epsilon, such that the probability that the absolute value of xn is greater than m is less than epsilon for all n greater than or equal to 1. So you can see this is saying that the sequence values don't get above m with very high probability. In fact, you can get that arbitrarily small because this needs to hold for all epsilon. Okay, the final thing I need to define is xn is big O of p, and we'll write this as xn equals, and then a capital O sub p of, I'm just going to go with the 1. That's all we need. But just like little o, you can put a sequence of real numbers in there. If xn is bounded in probability. Okay, I claim that if you take a little op of 1 function and you multiply it by a big op of 1 function, you get something that is little o of p of 1. This represents some function, some randomness, some random variable or function of random variables that is going to 0 in probability. This represents some random variables that are bounded in probability. So something going to 0 times something that's not blowing up should be going to 0, which is what it's saying over here. The product of those two things should be going to 0 in probability. Highly believable. I'm going to write this up for you and put it on the Canvas page because I don't know. I should have just committed and not done this kind of halfway. I should have either stuck with the n terms that go to 0 or committed more strongly to this. But I claim that if you take a little op of 1 function times a big op of 1 function, you get something that's little op of 1. Again, what that means is if you have something that is converging in probability to 0 times something that is bounded in some sense, the whole thing, that multiplication, is going to be converging in probability to 0. Okay, so with that, I think we can prove this. And I also think I could feel just a tiny bit better about n stuff goes to 0. Okay, so the proof of Wilks' theorem. Let's set some things up. I'm going to let lowercase l of theta be the log likelihood. This is a function of theta, but it's also a function of the random vector x1 through xn. But that notation is suppressed as usual. I'm going to let theta n hat be the MLE for theta. I'm going to let theta naught be the specific value of theta that generated the sample. We usually say x1 through xn or IID with parameter theta, but when we work with likelihoods, we're thinking of theta as a variable. We want to talk about the specific value that generated the data, and really what this comes down to is the probability we need to compute for this hypothesis test is something that happens when the null hypothesis is true. So under the assumption that the null hypothesis parameter was used to generate the data, we have the following results. I'm going to look at a Taylor polynomial expansion of the log likelihood. I am going to evaluate it at this theta naught, and I'm going to center it around the MLE. So I'm going to get like an L of theta n hat. Let me make this a little smaller. I'm too large for my own good here. Okay, plus L prime of theta n hat times theta naught minus theta n hat. Kind of doing this backwards. We're used to seeing the theta n hat and the theta naught reversed in roles here. Plus 1/2 L double prime theta n hat times theta naught minus theta n hat squared plus 1/3 factorial, or 6 L triple prime. And here's where I'm going to cut off the Taylor polynomial. So the point that goes in here is something that's between theta naught and theta n hat, and because theta n hat is random, this is going to be some random variable. So I have to say where theta n tilde is between theta naught and the MLE theta n hat, and therefore this needs to be a random variable. So I'm going to use this expansion, this Taylor polynomial, for the log likelihood. We can do a lot of simplifying here. For one, the derivative of the log likelihood evaluated at the MLE is 0. That's how you find the MLE. You take the log of the likelihood, you take the derivative, you set it equal to 0. So let me not make such a mess out of these equations. Just make a little list of things. So number 1, the derivative of the log likelihood evaluated at the MLE is always going to be 0. Number 2, under the regularity conditions, we have that our MLEs are well behaved, and in particular, they are consistent estimators of the true parameter theta naught that generated the data. And this implies that theta n hat minus theta naught, or the other way around, cubed, squared, or even to the first power, is converging in probability to 0. That's the consistency property of the MLEs. And the third thing I'm going to use here is that I'm going to say that the third derivative of the log likelihood evaluated at the MLE is bounded in probability. What we do know is that the third derivative with just a constant theta in it is bounded in probability, but this is more a stronger statement because there's something random plugged into our function that is based on random things. So that actually was not one of my original assumptions. I actually don't have time to show this. I will try to add this to my write-up, and I'm going to use this. Let me get to the real point. I'm going to take away that hat. I'm going to use this to show that when I put the tilde here, that random variable, this is bounded in probability. So again, I've only asked you to assume that this is bounded in probability. When you plug in that theta and tilde, is it still bounded in probability? This is something that needs to be shown, and I'll write it up for you. But let's assume that we know that this is true. We do know the first two for sure, just so I can finish this proof, and maybe even I can fit this in at the end of today. Okay, so going back to my Taylor polynomial and plugging in the 0 and the fact that this is bounded in probability, so this is a big OP of one term, and this is going to 0 in probability, so this is a little OP of one term. And I already claimed that when you multiply such terms, you get a little OP of one term. So this entire thing is going to be little OP of 1. It's not hard to convince yourself that multiplying by a constant is not going to change that. So what do we have? I've got L of theta naught equals L of theta n hat plus 0 plus 1/2 L double prime theta n hat theta naught minus theta n hat squared plus something that is little OP of 1 plus the stuff that goes to 0 fast enough. Let's look at the thing we want to look at and show it is chi-squared. This is minus 2 times the log of the likelihood ratio at theta naught over theta n hat, restricted MLE over the regular MLE. The log of this ratio is the log of the first one minus the log of the second one. But we have a notation for these things. Our log likelihoods, we denote with this sort of just L. And this is what I have here if I subtract this to the other side. So this is equal to -2 times this stuff. I've got a 1/2 there, so I will get a little bit of cancellation, and we'll get negative L double prime of theta n hat times this. It's squared, so I'm going to write it in the way that will probably make you more comfortable. Yes, I turn things around, but it's squared. Okay, so to make this look like things we might know a little bit about, I'm going to put a 1 over n in front. And then an n over here, but I'm going to put it inside the squared with a square root. We're about to pull out an old result for MLEs involving asymptotic normality. Okay, so this is going in probability to I1, the Fisher information at theta naught, by the weak law of large numbers. We used this back when we were talking about MLEs and all their asymptotic properties, but if you wanted to see this, note that the likelihood is the product of the PDFs. So the log likelihood is the sum of the logs, and the second derivative with a negative out front is the Fisher information term. And so this combined with this is the Fisher information term, and the whole thing is divided by n. So this is the weak law of large numbers. This is like saying that x bar converges in probability to mu, where mu is the expected value of one of them. It's just that for this problem, one of them is the negative second derivative of the log likelihood. Okay, and this other part here, let me write this whole thing a little bit differently. This is 1 over n L double prime of theta n hat. I'm going to put divided by I1 of theta naught, so that converges in probability to 1. And then in here, I am going to write this as theta n hat minus theta naught over 1 over the square root of ni1 theta naught all squared plus little op of 1 plus terms that are going away. So that's equal to the line above. I put the square root of n in the denominator with a 1 over, and I put some information terms in there so that they would cancel. But now we know that this is converging in probability to 1 by the weak law of large numbers. And this thing inside without the square is our MLE properly standardized. And we know this converges in distribution to a normal 0, 1. This is a property of the MLE theta n hat. Therefore, the entire thing, if you include the square, is converging in distribution to whatever a normal 0, 1 squared is, which is the chi-squared distribution with 1 degree of freedom. And this is by the continuous mapping theorem. If the thing inside the square function is going to a normal 0, 1, then the thing itself is going to a normal 0, 1 squared, which has the distribution of a chi-squared 1. Yeah, and there you have it. So to conclude, all of this came from this expression. We've got -2 times the log of the generalized likelihood ratio is converging in the weaker sense, this is Slutsky's theorem, to 1 times this chi-squared, I'll write it as a W, plus a 0. So to finish this up, what this is saying is that -2 times the log of the GLR is converging in distribution to W, where W is chi-squared 1, or we often just are a little bit lazy about that and say that it is converging in distribution to the chi-squared 1 distribution. Those are both saying the same thing. And all of this calculation, all the information terms and things that I standardized above were standardized using theta naught. So all of this computation was done under the assumption that the null hypothesis is true, which we usually abbreviate to be under HO. So under HO means under the assumption that the null hypothesis is true. I will write up for you this evening the some of the little o calculations that I used, like a little OP of 1 times a big OP of 1 is a little OP of 1, stuff like that. And also that the third derivative of the log likelihood evaluated at theta n tilde is bounded in probability. And next time, I want to do one more GLRT example, one more asymptotic GLRT example, and then we'll get into the review. But I wouldn't skip this problem on the final because I know it's something that looks really hairy, that is coming in fast, and we didn't have a lot of time to go over it. But look at the review problems. The large sample approximate GLRT is very mechanical, plug and chug. Do this, say this. So it's really an easy problem to get full credit on the final for. So we'll talk more about that next time on mathematical statistics.